This is the protocol of modeling of active thermography as a final work for the Bachelor in Mathematics. As advisors, we have Dr. Rumen Somchev, Dr. Martin Diaz-Viera, and Dr. Marlene Hernandez Ortiz at the University Open at a Distance of Mexico. Here we have the menu of what is going to be in this presentation, a short introduction, and then a description of what is going to be, and then some final remarks. Active thermography is an experimental technique consisting of using thermal data from a laser beam pointed towards a sample on its original state. The methodology that is going to be used for this work includes the conceptual model, which are the hypotheses, postulations, and conditions to be satisfied by the model. The mathematical modeling is the formulation of the conceptual model in terms of equations. The numerical model, which is the discretization of the mathematical model by the application of the appropriate numerical methods. And the computational model, which is the computational implementation of the numerical model. We are assuming stationarity and isotropicity. Heat is provided uniformly onto one or more surfaces. The differences of temperatures between the environment and the sample is small. The convection can be represented linearly. The exchange of energy can be represented by convection, conduction, and radiation only. There are no chemical reactions nor loss of matter, only loss of heat, and this last is lost to the air mostly. Gravitational potential is negligible. Temperature of air is negligible for the model. The equation and boundary conditions obtained after the energy balance are these equations on which we have, in terms of temperature, the convection term, which depends on the area and the convection parameter, the radiation terms, which is the fourth power of temperature, the function of temperature and emissivity area, and the radiation parameter, and lastly, the Fourier equation for the conduction, on which we have lambda, which is the parameter of conduction. Upon choosing two boundaries, we have these possibilities. Here we have these two boundaries on which we will have Neumann boundary conditions, where we are going to inject the power, and we have two cases: either they are equal or they are opposite in sign. And the other boundaries are zero in terms of injection of power. They are merely going to radiate energy. The discretization of the mathematical model entails, for the time derivative, it can be used as second-order backward finite differences discretization, resulting in a totally implicit scheme in time. For the rest of the differential operators, concerning the spatial derivatives, it can be applied as standard Gagliorkian finite element discretization, where Lagrange quadratic polynomials can be used as weighting and basis functions, which in this work imply a convergence of order 2, according to Sienkiewicz et al. 1977. A regular mesh of triangular or tetrahedral elements, respectively in 2D or 3-dimensional, can be used. For the linearization of the nonlinear system of equations, an iterative Newton-Raphson method can be applied. For the solution of the resulting algebraic system of linear equations, it can be used a variant of the direct LU method for sparse unsymmetrical matrices. The COMSOL equation is what offers the COMSOL multiphysics system. So what we have shown as the equation in terms of temperature can be adapted to the COMSOL equation using scalar expressions to define the coefficients. In this figure, we show this menu in COMSOL, where the subdomain settings is where the coefficients of the COMSOL equations are written using the definitions of the scalar expressions. Two boundary conditions types are needed: Dirichlet for most boundaries, and Neumann, the input of power. And in this figure, it can be seen the Neumann boundary conditions at these two extremes, and the Dirichlet boundary conditions for the rest of all the other boundaries. The meshing is physics controlled as per default in COMSOL, which can be seen in here, with a so-called normal size in the elements as per default in COMSOL multiphysics. As a final remarks, we make a summary of this work. It is proposed that with experimental data from active thermography, make a numerical fitting determine both experimentally and with theoretical modeling the thermal properties of different materials and the heat loss from the material under consideration. That is to say, we are going to move numerically the parameters until we have a best fitting of the partial differential equation developed for the mathematical model and implemented in COMSOL multiphysics. The tentative title would be for this work, Modeling of Active Thermography. These are the references, which entails the lecture notes in mathematical, numerical, and computational modeling of flow and transport in porous media for the postgraduate studies of earth sciences in the National University of Mexico City. And the second important is the Sienkiewicz, Taylor, and all others as the finite element method, which is the numerical discretization of our mathematical model. Thank you for your attention.